Thank you. And first of all, let me just thank the organizers for this kind invitation. It's a really, really great workshop. Yeah, and such a venue, such a view, right? In the window. Okay, so I'm primarily doing network things, and when it comes to evolutionary games, my interest remains mostly on network. And today I want to present one project which I recently completed, and then these two guys, he's the associate professor in Beijing University, and then his student Yao. So they were the main workforce. So who they say the all the work. So in neuroscience, in the intersection between neuroscience and evolutionary game theory, so there are some many neuroscientists who started to work on the evolutionary games around 2005. Of course, there are some papers before this period, but one of the papers which people in neurosciences, or associated complex system studies find the major is this series of papers by the Francisco Santos and the Jorge Pacheco. Yeah, Fernando's advisor, as far as I understand. Okay, so they did the numerical studies on to run evolutionary games on scale-free networks, which mean that these degree they are heterogeneous. Some of the nodes have a very high degree, whereas others don't, and this represents the features of most of the social networks. So in that sense, this is realistic. And what they found is that follows. Okay, so this is how they parameterize the present dilemma game, and then this is T and this is S, and then this part corresponds to this present dilemma. Well, we saw some similar figure yesterday as far as I remember. Anyways, what they did is that this is not a scale-free network, so everybody has the same degree, versus this is a scale-free where some nodes have a very large degree. And then this red means higher cooperation. So if you look at the present dilemma, or even this node drift game regime, or even star hunt, so they see the enhanced cooperation, because this is a bit more red in a wider parameter region than this one. Okay, and then this is sort of very to my eyes. So this is very different from what we understand from the fixation cooperation. Okay. But there's a basic assumption. So this is numerical, and then this is strong selection, and then they are looking at this equilibrium density rather than fixation probability, right? And of course, there are further assumptions, but I can say that still, many people's work, in particular in neuroscience related fields where the people do study this evolution game, dynamics, are based on this understanding. But of course, there are many assumptions. For example, one prominent assumption, which was challenged by many people now, is that how to determine the payoff. So the hubs, the large degree node have many neighbors to play the game with, right? And then the original the game, that's the paper like this. They accumulated the payoff across all the neighbors. And then on the other hand, the low degree node has only a few players to play the game with. So in that way, there's some asymmetry between how many these neighbors they can accumulate the payoff over. Okay, and if we normalize this, we don't see cooperation. This is one example to show that this is how difficult to consider the evolutionary game. Consider evolutionary game dynamics only heterogeneous, degree heterogeneous, irregular networks. And then more recent studies, by this Alex and Ben and Martin Novak, showed that different payoff schemes. Good schemes will be important. So this is these two topics I don't consider in this talk, but here, so I'm more focused. But there are the two examples of why I say narrow games are difficult to consider, or at least it should be considered with care. Here, so I focus on one thing, which is to compare this equilibrium density view versus the fixation probability view. So I know that most of the audience here are more versed in the fixation probability dynamics. But at the same time, like I said, the equilibrium density is something people look at. So let me just start from this paper by Hisashi many years ago. So this paper is the theory, and the first this type of theory to show the fixation probability on the networks. But he assumes regular graphs and developed the pair approximation theory. So this theory itself doesn't account for what happens for the scale-free networks, but nevertheless, he did a simulations. And this simulation shows that, okay, this is the baseline, say, the fixation probability. So if this is larger than 0.01, because the size of a network hit used was 100 nodes, and then the 1 over 100 says this. So if this is larger than this fixation probability, this means that, say, the cooperation is enhanced. And then the cooperation is enhanced, I mean, less for the scale-free networks. So this is a different degrees, but as compared to these regular lattices of the same time, this is the most difficult to see the cooperation because, I mean, okay, these, I mean, arrows come from his theory, but this theory is for these regular graphs. So this position of this arrow and the position of this arrow are the same, okay? And then if you compare where this crosses this 0.01 line, so this is more to the right. This means that, say, it has to have a, say, larger benefit to the cost ratio. So this clearly shows us in scale-free networks, it's more difficult to get than the cooperation. So this is a bit different view from this equilibrium point of view, which people have been doing numerically mostly since 2005. So this is a, say, paper by Ben. So this paper allows us to, say, compute the fixation probability for arbitrary graphs, okay? And then this is the mean degree. Okay, so the mean degree small means, I mean, this cooperation threshold becomes small. So if you go down here, so this means, say, the cooperation is easier. But this is not what I focus. So if we put, the fix the mean degree and look at the different graphs, because these are acronyms, but overall, the scale-free networks are here. Of course, I mean, this RR is different. So it depends on the network model we use, but the overall, scale-free networks tend to have a larger value of this. Versus this ER and SW is a relatively, say, degree homogeneous networks, which are sitting around here. So this is another indication that the scale-free networks make the cooperation more difficult. So the question is this: so what do the scale-free networks do? So for the fixation weak selection point of view, so there is a unique answer. So given by these two papers and many others, which is that the scale-free networks makes it difficult. But this is sort of, say, the opposite to what, say, the many complex systems, see, people are doing in, say, the numerical simulations. So our, say, the claim is to say that if we, say, look at the temporal networks, and then consider cooperation and develop theory. So this can unify these two, apparently, the seemingly opposite views. So for this, to this end, so we try to, say, develop a temporal network theory to explain this phenomenon. Okay. So temporal network is something I work on a lot. So apart from the evolutionary game theory, not necessarily. So there are, say, the network science, there are, say, tons of people, say, doing, say, including myself, to do, the time varying network, and this still remains a hot topic there. So for this reason, so many people have been, say, doing the temporal network, say, evolutionary game somehow. And this paper is one of such early papers. It's a numerical study, and it happens to be done by my previous postdoc in Bristol, UK, when I was there. But this work was this guy also said he did this, but he did this before he joined my lab in Bristol, okay, UK. So what it shows as follows. Okay, so there's a different ways to construct temporal networks, and this figure is similar. This aggregate network means that, say, there is no temporality. So this static network. And this figure is same as the Santos Pacheco paper, which I described. So basically, we want to see how large the, say, red-ish region is. And then particularly the Poisson dilemma corresponds to this fourth quadrant. Okay, and then this is, say, higher resolution time, the temporal network. So this clearly shows that the cooperation decreases as we introduce the temporal network. This is natural in the sense that the temporal networks means that, so if I believe that, so this is the neighbor, in the case of studying network, we have this neighbor forever. So we can, say, form a pair correlation of cooperation. However, if the network, say, is just changing rapidly, then okay. So even if we establish C and C right here, but this person becomes non-neighbor at a later time. So we lose association. So in a sense, it's natural to say that less cooperation in a temporal network. But this is the very things which this paper showed in under some setting. Okay? And then to do theory, so we need some modeling strategy. And then I think, so there are, say, two, say, main modeling studies to try to do these some theoretical work on, say, the evolutionary games, and also on other dynamics such as the epidemic dynamics on temporal networks. One is to say assume. This is what we do. So this one is to assume that it's a network changing at the constant intervals from one network to the other. So we use each time for time tau and then switch to another. This is one strategy. And then there is a reason for that I'm going to explain later. Okay. And another strategy is this. Actually, it was employed by this the Chisu and Alex and say Josh's paper a few years back. And so also say some people in say epidemic dynamics on networks, I mean, doing say control theory, whatever, they do the same strategy. I didn't cite the paper, but they do did the same. So the point is that it's okay. We prepare say the certain finite set of networks. Let's say we have 5 networks. And then the say network say performs a random Markov say process to transit from one network to another at a random interval. In this way, we can model the Markovian dynamics of networks, which is amenable to this analytical analysis. So these are, I think, the 2 main strategy. But in this say work, I take this first view. So this is not new. So the people have done this, particularly Samin. So my main collaborator, I introduced his photo already. Did this for this equilibrium point of view. So he used say one say network for the G rounds of evolutionary dynamics and switched to another and switched to another like that. Okay, and then this previous work showed that looked at the equilibrium fraction cooperation. So this is not fixation. And even though I don't explain this, in the paper too closely, but this shows that okay, if we do that, and then the evolution of cooperation is enhanced by the temporal networks. And this does not contradict with this paper because this uses a very different assumption on temporal networks, which I'm going to introduce only in the last conclusion slides to see the future work. Okay. So this is our understanding. So we have studied network, temporal networks, and equilibrium point of view versus fixation point of view. And then this, Santos Pacheco said that this cooperation is enhanced, and temporal network, yes, the case. And then about this, if we look at the fixation for the studying networks, the scale-free networks, they suppresses the cooperation. And then we want to explore this case. And it sounds like we have a 2x2 table. We want to fill one. So this is the not the way I want to promote this and work on. But in the end, we started by filling this missing cell and think about the implication of this. Okay. So what we do is as follows. The network is the same as in the last slide. So we use this one network, and then actually we sample the edges for the analytical attractivity from some static network. Okay, we have one static network, and we randomly sample edges to create one network. And then we use that network for G generations. And then we switch to another network. But this another network is again the sampling of the same number of edges from the same static network. But of course, random sampling makes the network different from the previous one, right? So this is how we did this to make the analysis possible. And we want to see whether cooperation evolves or not, right? In the fixation probability sense. So we have a usual assumption. We have the usual assumptions like the weak selection. And we start from single cooperator and say N-1 defectors. And then importantly, we use constant switching networks, right? But in the switching interval, it remains constant. And the G rounds for each, this network before it switches to another network. Okay, here's the main result. So we developed the fixation theory for this case. We used some approximation, but we still did, okay? And then in short, the result is that this scale-free temporal network promotes cooperation. And then I think the figure summarizes the main results. Okay, let me just explain how we read this. Okay, it's a bit complicated figure, right? So in the case of studying networks, this is not new. And then this is consistent with these previous papers. And then how we do this is that, so we look at benefit ratio cost, and this is a baseline. So if it goes beyond this, we said the cooperation is enhanced. So we want to look at the threshold at which B over C passes this 1 over M, the baseline. And if this is lower, then this means that the lower fixation, the lower benefit to cost ratio enables cooperation. So this happens easier for this. This is a regular random graph, so there is no degree heterogeneous. Everybody has the same number of neighbors. Versus, this case is a scale-free network. Some people have a very large number of neighbors. And scale-free networks, as expected, makes the cooperation more difficult by shifting this threshold B over C to the right, larger value. Okay, this is expected because it's known. But in the case of temporal networks, this makes it easier. So this is the regular graph, and this is scale-free networks. It shifted to the left, right? I mean, yeah, we just did this part. If you extrapolate this, I mean, it will be around here. So this is a much enhancement. So if G is larger, then say we get this, and if G is smaller, G is the number of say rounds in each static network before switching to another network. Okay, so we verified this over various scenarios. I mean, including on the various, let's say, the empirical networks. And the G is a free parameter, but the result does change quantitatively with respect to G, but not qualitatively. Even if the scale of the time scale of the game and the time scale of evolution is flipped by assuming G less than 1, it's still fine. Okay? So the last thing is why this happens. So the key insight which we relied on to explain this phenomena is as follows. Okay, so the heterogeneous networks are usually the bad for fixation of cooperation, like I said, and people have shown before. However, so if you think about this, how the epidemics dynamics spreads in networks, so we know that in scale-free networks it's faster. It's a very, very famous phenomenon. Okay, and then it's likewise. So if we think about this fixation speed, no matter which fixates or cooperation fixates or the deflection fixate, the speed of this is faster than degree-heterogeneous networks. And this actually has something to say about this cooperation. In the last few minutes, I want to explain this and then conclude and say, let me see in the future. Okay. So here I want to outline. So I don't want to explain all the details of the theory, but just outline the strategy of how we did the math. Okay. So we basically look at this, the probability of having n cooperators. If this reaches, the capital N, which is the number of agents in the network, then we declare that the fixation has been obtained, right? And then we discretize time in the sense that we look at this. So if one network is used for G generations and another network is used for G generation, so we can map the situation of the status of the network into the map. Okay, this is the mth application of the mth switching period, right? The start of the M network, right? And after G generations, then we finishes these G generations. But this is again the start of the next, this network, which is the M plus first network, right? And we can create this map between these two probability distributions, how many cooperators we have basically, right? At the start of each snapshot. And this is a discrete map. So by analyzing this map, we can we can consider how this N means fixation cooperation, because capital N means that we have all the capital N agents are cooperating, right? So we want to have this quantity, and this is a map, right? This is a map from this to this with some details, which I think I need to skip. And then we want to have this. So this is a strategy, and we can look at this property of this map. And this is a common strategy, not only in evolutionary games, but it has been employed. Well, we employ this in to understand this epidemic dynamics of networks. And then the epidemic dynamics, we don't discuss this fixation, but still this analysis strategy remains similar. And then so we can do the discrete time version of that. So the idea is that to map this, switching dynamics to exploit the switching period, the constant, into the maps, right? That's the idea. And also this part, I don't want to touch upon this too much, but the only one thing I want to say is that if you look at this each generation, right? So each of these, so we have a large connected component and some small small connected component isolated nodes. And then the evolution dynamics occurs only on the largest connected component. Well, there are some small components, but in networks, approximation is that the small components are really small, and most of the things are occurring on the single largest component, which dominates the whole thing. So this is the sort of physics understanding of what network does, and then not necessarily temporal, but also static network. So we use this to only consider these dynamics on that. Okay, the largest connected component. This is this part. So in short, what happens is as follows. Okay, scale-free networks is bad for cooperation when it comes to fixation probability. Okay, and then however, the scale-free networks realize the faster strategy dispersal, and then we can estimate theoretically. So we have some theory. So to say that this is a coalescence, but basically the strategy dispersal time is the proportional to the fixation time approximately. So we can use this as the say replacement of fixation time. So this means that okay, in scale-free networks, the fixation time is shorter than the fixation probability. So this is a sort of tug of war situation. So which effect is larger than the other? We just look at this. For example, fixation time is indeed smaller for this degree heterogeneous network, which are these two, as opposed to these two. Okay. And then this balance, the balance of the two factors determines which one wins. So depending on the parameter, so indeed the fixation becomes smaller. But if we are considering the temporal networks as we model this, so in most cases, I mean this faster dispersal factor wins, so that the fixation of cooperation happens despite that if you look at each single, say, scale-free static networks, the cooperation is suppressed. So this is a conclusion. So we found that if we look at this a bit holistically to allow the network to change, then we can sort of erase the apparent contradiction between what the scale-free networks do for the cooperation from the equilibrium point of view and the fixation probability point of view, to say that in both cases the scale-free networks enhance cooperation. Okay, this is the main message. And then switching, say, the temporal networks is useful, say, the machinery. And then however, so I'm interested in the following. So let me just pitch this to finish. Okay, so in the temporal network studies, the data are usually provided in this way. So we do this mathematical modeling. So we don't use this, but this is the one. Say this paper has nothing to do with the evolutionary dynamics or even any dynamics, but this is data. Okay, so this is where for example, these two people meet, right? And they are recorded as an event, right? And then this is the original data, which most of the social related temporal network are provided. So if we take as a time window to average them over, right, and we get the switching networks, that's fine. But originally, so I want to think about this probability that we can play the game on each event. But of course, this is difficult because I mean, different edge pairs have a different number of events and so forth. So I have been thinking about this problem for a long time, but I don't have a solution. But what is a nice way to theoretically model this into the evolutionary game theory? So this is something that I sort of interested in. Okay, and also this the whole machinery may be useful for using being used for the other dynamics than this evolutionary. Well, I know that this evolutionary game workshop, but still, I mean, like an epidemic spreading of opinion formation. Okay, and lastly, so I'm also interested in the fixation probability versus equilibrium density catches my attention. So if there are some scenarios, it doesn't have to be network. I mean, where these two views provide us the different results, qualitative different results, and then I would like to think about this. Okay, so if you have any ideas along this line, so I'm very happy to discuss. So thanks for your kind attention.
Time for one question here in the transition. So can you clarify what G means? G is the number of rounds between the switching events.
Yes.
It seems to me that if G goes to infinity, then it should be static. But that limit is not what the figures that you showed.
That's true. So this is one confusion many people have. So the G actually going to 0 is the limit of the study networks. It's very tricky. G going to 0 means network. The change is infinitely fast, right? So then we don't see the network change because it's too fast. And this is called the blinking network limit. Mathematically, this corresponds to study network. And if G is very large, yes, it's like a static, right? However, so it's network switch to another one. So this doesn't correspond to the study network limit, even if we send G to infinity. It's very tricky. I agree.
Thank you.
Yeah.